So we'll get started. My talk is concurrency patterns for high-performance Kotlin servers. I'm Bowen from Google Ads team. And this is a talk from the experience we have building Kotlin servers in ads. So Google Ads has a long history of building server applications in Java. And in recent years, more and more teams have adopting Kotlin, and including my team, and for good reason. As Java developers, we already know how to build high concurrence servers. So we use in the past years. We have using the Java toolbox, solving the concurrent problems in production for many years, including threads, synchronized blocks and shared mutable memories, thread local features, executor services. But the problem with that is those concepts are pretty low level. They're talking about very low level things, right? It's not exactly the concurrency toolbox. It's about how to execute code in parallel on your machine, on a particular machine. So there is a concept gap between your real world concurrency problem with those tools in the toolbox. So that creates a problem. That creates a discrepancy. Kotlin, on the other hand, gives you a much higher level concepts, much higher level toolbox. So you have the suspend function, you have coroutines, you have the coroutine scope, and which powers structure concurrency, and you have very high level code construct called channels and flows. Those are pretty descriptive and could be used to describe very high-level concurrent concepts, and we use that concepts to build the high-level, concurrent logics. So that's an advantage of the Kotlin toolbox. But the problem is that those are new. Those are new things, even for the jaded Java developers. And whenever you are facing the Kotlin landscape, it's a bit intimidating by looking at the individual concepts. And even if you're familiar with every single one of them, it can be a little bit challenging to fully comprehend them and use them to create a reasonable implementation for your real-world applications. So this is how I'm here trying to fill the gap, and this talk is heavily inspired by Rob Peck's Go concurrency patterns in Google I/O 2012, I believe. It uses patterns to trying to not give you a set of APIs, but instead give you a lot of repeated small code pieces that you can reuse to construct your program. So the key point is like how you structure your program, not just understand the APIs, right? So here's how we go, how we proceed with the talk. We will use the slides to introduce the shapes of each patterns, introduce the pros and cons of each problem, and we will switch to a notebook to give you a live coding experience. So that live coding is important for this talk, mainly because concurrency concepts is really hard to describe on paper. You have to see it in action. You have to see the results, and especially concurrent naturally is non-deterministic. So you need to see run the program a couple of times to see the different result and see the characteristics of each pattern. All right, and each section will change one part of the server pipeline, so we don't have a lot of things together. We will solve one problem at a time, piece by piece, step by step. All right. And quickly review the concepts used in this talk. You already listened to those concepts many times, so I just be brief. The coroutines is just a lightweight concurrent work with sequential looking code. And it can suspend and it can pause at any time if you are doing some blocking work. We have the structured concurrency used in this talk. So structured concurrency means you have a group child works into a scope, and whenever you cancel the scope, you cancel all the child coroutines. So that's pretty much lifecycle management. All right. We have the channel. It's a way of communicating between coroutines. All right. Channel is a pretty useful construct in Kotlin, and it's highly optimized for doing this cross-coroutine communication. So you shouldn't ever use shared memory anymore for communication. You should use channels. Flows are streams of values that can be become available whenever they're ready, and it's pretty much a reactive stream, but in the Kotlin flavor. And also one important caveat is that Kotlin flows are by default code. You can have hot flows, but that's separate topics we are not covered here. All right. So before we go into individual patterns, I want to quickly use a small demo to show off how those Kotlin tools perform it. All right. So we use a Chinese whisper example by codies. All right. So we are going to have a whole bunch of codies. Each codie speak to the next one, give the next one a piece of information, and the next one maybe modified it a little bit and pass on to the next one. So we will have a lot of codies created as coroutines, and we will see how fast it is to do the whole thing. And we'll show you the code quickly. This is how simple it is to describe this kind of high-level concept in coroutines, in Kotlin. So we will, to make it challenging, we will make like 100K stages, 100K codies, because why not? All right. The first codie will just send one to the next one. All right. It's a initial value, and for the rest of the codies, we will just listen to the previous one, plus get the number plus one, and send it to the next one. All right. And finally, we collect the numbers and print it out. All right, so we will run the code. Before we run the code, any guesses how fast it can be? Any guesses? Wild guess? All right, let's give it a try. That's it. How much is it? 124 milliseconds. All right, that's I would say that's insane efficient, that's insane fast. Because think about that. What we have, all right? We have 100,000 coroutines actually started. Each coroutine starts the flow, and that flow is a channel flow. Means we actually started 100K channels as well, and we pass the value through those 100K channels, one by one, all the way to the last one, and then we print it out, and after that, after the program finishes, it has to clean up all these things. All right, so that also counts into the 124 milliseconds, and all that can be done in 124 milliseconds. So that's on my machine. But it's it's give you a concept of how fast it is. So next time when you are trying to start a coroutine on the server, you shouldn't feel exotic because you can just start coroutines and start your asynchronous work and don't worry about the performance. Like, is there any penalties on the performance? Because if you're from the Java background, you know starting a thread is pretty heavy. That's why we have thread pools. That's why we have the executor services, right? But in Kotlin, using coroutines, you shouldn't worry about it. Just start coroutine and let the Kotlin handle the rest. All right? So here, let's let's set the stage for this talk. So we were going to set up the demo. We will, assuming we are building a assistant server, the assistant server takes a prompt from the client and call the model, and the model will return. This is a fake model we are going to use. It's just a simple implementation and return a list of things. Like some of the responses just a plain text. Some of them is more complicated. It's a tool call, like generate image, search for some terms, or search for some even more terms. I should say 2.4, but you get the idea. And maybe load some files based on the prompt, and then we will compose all those into the final result sent back to the client. All right, that's how we want to proceed with it. So that means our server need to run those tools as well. Run tools typically means like you make RPC calls to some backends because search could be implementing different server. What else? Generate image could be in a dedicated image generation server. But here we just make it simple. We just fake it. We give it a fake latency. Arbitrary latency. And we have some fixed chunks. We'll see, okay, if you generate image, we will send it back 10 blocks. If you search file, we will send it back like certain amount of blocks. And this is implementation for it. Different tools is just a function call which have different delays and different number of chunks returned. And for each chunk, we have different string format for that, so you can tell which one is which. All right. So let's use that to start the baseline implementation. The baseline, we don't have any specific patterns applied. We just want to show if the brute force implementation would look like. So here, we would have the resolve function used by our server to resolve each of the model parts. Obviously for the tool call parts, we need to actually call the tool. For image, we'll generate image. For search, we'll search, et cetera, and send the results as string, as a list of strings. And for text part, we'll just send out the original text. All right. So here's implementation for the baseline implementation. It's simple. Call model, flat map, because we return a list of, for each model part. So we combine them together and produce a final list of strings. Let's do it. Oh, here's just some examples showing what the output would look like for the tools. All right. So we will have here's a baseline implementation, and it took roughly 2.5 seconds to finish the whole thing. And you can see everything is listed as its original order as the model produced, except for the tool is replaced by the tool call responses. So far, so good. All right. The problem with the baseline implementation is that the client only get all the responses until all the responses is ready. it cannot get the responses as soon as they're ready. So think about that. We first call the image generation tool. So supposedly you should see the image generation results coming out, and clients should be able to process that. But that's not the case for the baseline implementation, mainly because we collect everything on the server side. So to solve that, there's a pattern we can use. That's a generator. In Kotlin, a generator is just the function that returns a flow. All right, a function that returns a flow. It seems trivial, but it has. If you think about that, if you think of it this way, you will see this pattern repeat itself in many times. We'll see that later. So a function returns a flow, gives you the ability to emit the results as soon as they are available. So here, the new result, instead of to list, collect them to list, we emit a to response right away. And the handle response right now will emit the whatever information, whatever chunks that's produced by the new resolve implementation. All right. So let's give it a try. Here we go. Yep. As you can see, so the outcome, the output isn't show up at once, right? So it produce one, output one, produce one, output one. So that's how the generator allows you to do, like make the result available as soon as possible for the clients. So the client has the chance to take action on it. Sorry. Let's go back to this. So this is still good. What it achieves is a reduce of the first byte of the time to the first byte for the client, but the overall execution time is still pretty long, right? It still run the tools in SQL, so it doesn't reduce the overall latency. To reduce the overall latency, we definitely want to run those tools independently, because why not? Those tools are independent to each other. There's no dependencies. So that gives us the next pattern. That's Feng. What Feng means is we have multiple producers. Each producer will shout out some information, but eventually those information will be collected by one final stage producer, and that producer will produce the final results. So you can run multiple things concurrently, and then produce just single stream of output. So here's how we do it. In Kotlin, it's pretty straightforward as well. Remember, patterns doesn't have to be complicated. It can be very simple, but the point is like you recognize those patterns and trying to reuse them in different ways, in different places. So here, what's significant is that we add a launch call here within the channel flow. So remember, channel flow has starts a flow and starts a channel as a communication mechanism, and each of the sub-coroutines launched by this channel flow has access to that channel, and you can send the result to the channel, and then the channel will eventually send it to the client. All right, so this is pretty powerful setup. So the Feng allow you to combine multiple concurrent works and produce a single stream of output. All right, so let's give it a try. All right, so as you can see, the overall latency, that's a little bit harder to read, but it's here. It's about 1 point some seconds. That's far less than 2+ seconds. We definitely get some overall latency improvements over here. But now the results is different. The results, like all the outputs from the different tools interleaved with each other, that mix together, because right now things are running concurrently, and those information become available as soon as they are produced. So there's no control over like which one comes first, which one comes next. So is there a way to restore the order while still keeping the benefit of the concurrent logic? That comes to the next pattern, trying to ordering on the server side. So obviously, this is one way to do that. We can, instead of sending back whatever information as soon as possible, the server can try to restore the order. The key point here is that instead of emit the result from the tool call as soon as possible, we first start a whole bunch of tool call coroutines and collect them into a deferred list. And then we go through the deferred list in its original order and collect them one by one and send the results after the results become available. So as you can see, the benefit is that we definitely restore the original order, but potentially the client won't see the second or third output until the first one is outputted. But at least we have the benefit of running things in concurrently, but still getting the response in order. So let's see that in action. Here's the results. You can see the result is still outputted gradually, not in one bunch. But that's because we have the generator. And also, we have the things ordered naturally as before. And the timing is off, right? Did you notice that? The timing goes back to 2+ seconds. That's not what we need. Main problem here is, can you spot it? Anyone? Why the latency goes back? It's supposed to be running concurrently, right? I'm sorry? You need a array for await. Await is on the fourth line, right? I will switch back to the slides. This is await, right? So we definitely await. Oh, you are saying await is causing the problem. Async is launched lazily. No, async is starting the subcoroutine right away. Right? There's no surprise here. Async is async. It starts the coroutine unless we tell them don't start immediately. There's some control over that. So actually, what happens here is this line, specifically resolve 2. Did you notice that? Resolve 2 returns a flow. But the flow, as I said before, it's code. So whatever trying to produce in the flow, like the tool call, is not executed in this coroutine. So the coroutine returns that flow, but that's it. It returns a code flow. It returns a blueprint of what needs to be done, but it's not done when the coroutine returns. So what happens next is that when you await, it returns a flow, nothing is done. And then when you collect, that's when the first flow is actually doing the work. So the second and third and fourth flow hasn't done anything at all. So you can see everything is still running sequentially. That's a problem. That's a pitfall we run into a lot of times. So the fix is pretty simple. See, in this line, within the coroutine, within the subcoroutine, we have to collect the flow. toList is a terminal operator for flow. Whenever you call a terminal operator, it collects the flow. It exhausted the flow, trying to extract all the data from the flow and until the flow is closed. So that pretty much making sure whatever work need to be done by the flow is done. All right. So in this case, when the subcoroutine returns, all the work need to be done by the subcoroutine is done. All right. So everything is the same except for this line. So let's see. All right. Back to normal. So this time we have much faster executions. That's so far so good. We do the server-side ordering, but as you can see, a client doesn't get information as soon as possible anymore. So that might not what you need. If you need a client-side ordering, there's additional effort you need to pay. All right, so you can do that by sending back the sequence number, or in general, some additional metadata. All right, so that can be used by the client to know which chunk should be placed at what position. So here, we are going to send back a response class. Each response has a sequence number, and we have a whole bunch of different response types, as usual, text, image, search results. We do that mainly because we need to send back additional information to the client, so the client be able to construct the order. And we have to add a done marker just to let the client know, okay, some of the two output is done. Otherwise, from the client side, they don't know the flow, so they won't be able to know if this chunk is the last chunk. So we need to synthetic that. All right, so this is a new implementation. What we do is, just convert each of the two response into the new responses and send it back to the client. So here we go. Let's see the responses. All right. So as you can see, we already have additional informations. So what do we do with those information? All right. Most straightforward way is just sort it, right? Once you get all the information, but it's not really hard to imagine. Your client can place some placeholders if you are doing some GUI work. Put some placeholders for the image and put the individual image chunks as soon as they become available. So this is what client-side rendering offers you. All right, so we have the ordering, but there's one more thing for the this kind of remote request calls. That's timeout, because usually the client won't wait for your response forever, right? So there's some limit. One simple way of doing that is just to have a coarse like whole request deadline. We can do that pretty simply, pretty easily with Kotlin, mainly because the Kotlin coroutines and Kotlin suspend functions are executed sequentially. And even if the suspend function can be suspended and resumed, it doesn't mean the execution flow goes to somewhere else. It's still here, so you can wrap the whole thing with timeout, and with the timeout, and also capture the timeout exception and print out the results. All right, so let's give it a try. So we see it timeouts. Give another try timeouts. Even because the image generation is always a problem, so it will always cause a problem. If you run it enough times, it will eventually succeed, because sometimes it will succeed successfully run everything within the timeout. But again, this is a little bit blunt, because as soon as any of the two timeout, the whole process will be canceled. That's might not what you need. So you want a finer granularity control of the timeout. That's still easy to do. And when you do that, you find you are repeating the same patterns just in different level. All right, that's the beauty of the Kotlin approach. So here, we still have the original approach. You can see a deferred list. All right, this is still having the bug but, in the threads. But the point is, like, you can wrap the individual tool call in the timeout and capture the exception, same as previous threads. All right, so that's the same pattern over and over again, but you can use that in different levels to achieve different granularity of timeout controls. So let's solve that. Lab. All right, don't ever do that again. What happens? Oh, okay. Good call. Yeah, we have some lab bug fixed. All right, so here we go. You can see the timeout here, but you still get all the results and the final, the end output here. That's nice. But is there a way to eliminate the timeout altogether? Because if you give it enough time to run it, it will eventually succeed. So it's not a very pleasant experience if your call sometimes succeeds, sometimes fails. You want to have a more stable results as much as possible. So that's where you can do request hedging. All right. The concept is pretty simple. Request hedging is you send multiple requests to, you send the same request multiple times, preferably to multiple replicas if you have, but even sending to the same replica, it might give you a better result too. So here, we just, in the new resolve function, in the hedged resolve function, we start a channel flow. And within the channel flow, we repeat 5 times, actually. In the code, we repeat 6 times. Whatever number suits you, suits your situation. And for within the repeat, we just launch a new coroutine, send the result back. So as you can see, we pretty much start 5 coroutines doing the same work. And whoever finish first wins. So here we have the channel. That's remember, that's a generator pattern. So we have this is a find-in pattern. So we have started multiple coroutines and we collect with the channel flow. And the difference here is, like, we have the first operator here. The first operator will try to get the first results and cancel out the channel flow. When they cancel the channel flow, whatever slower process is still in progress will be canceled with it. So that's a structured concurrency gives you out of the box. You don't need to worry about any of that. All right, so the server implementation would be pretty straightforward. Just use the new implementation, and it should work for you. All right. So let's see how it goes. Request hedging. Do we have timeouts? No. Here we go. So if you run again, we should see far less timeouts happening all over again. Remember, this is an honest demo, so we don't have any code here. So as you can see, if you run it enough times, no timeouts. So that's request hedging. And request hedging is actually built into many of the server frameworks, or maybe if you use gRPC, gRPC has a request hedging built-in as well. But if you don't have that in handy, this is what you can do as a Pullman's implementation for request hedging. So far, we only talk about the server side. What about the client? All right, so the client, we only use the printf as a client. The printf is pretty fast, but in real world, the client can be slow. Like the client, not necessarily is a cell phone, is a browser. The client can be another server. All right, another server consumes the results from your server, and that server might doing some heavy work as well, or maybe it's sending requests and waiting for some other request, waiting for some of the responses and blocking there. So it doesn't have the capacity to process whatever you are producing. So if you are sending the results really quickly, it has to be cached in the client side somehow. And if the client side don't have enough memory, that would be overwhelmed. All right. So let's see. So that's when you need some way to control the the server and the client cooperation. So let's use this to simulate a slow client. We have a client delay 180 milliseconds and print out the thing. So it's definitely much slower. And the pattern we are going to use is backpressure. What backpressure means is not only when the server sending back the response to the client, it's no longer a one-way communication. It's a two-way communication. The client has to somehow tell the server, like, I cannot keep up with your pace. Please slow down. Please don't send the next response until I tell you ready. And that can be simulated in Kotlin pretty easily using flow, because flow naturally has a backpressure mechanism built into the implementation. So it only produces the next response until the previous response is consumed by the client. It's collected by the client. All right. So let's see how this one goes. So instead of collect, we use the collect slowly, which is defined, all right, which delays a couple milliseconds. All right. So yeah, as you can see, it's pretty slow. But the significant part of this output is, if you select the server, you can see the server output and the client output interleave with each other. So that means the server won't do any, won't move forward, won't proceed any further if the client hasn't consumed the previous response. All right. It has its benefit that definitely the client won't be overwhelmed, but the performance drops a lot because when the client says, "Okay, I'm ready for the next bit," the server hasn't started work yet, so the server still needs to spend some time to produce the next response. To improve that, we can have the buffered backpressure. It's simple in Kotlin. You can add a buffer operator to the flow before it's consumed. All right. Here, just add a capacity of 2, meaning the server will produce 2 more responses ahead of time before the client is consumed. That should be benefit enough that we can get most of the both world. Let's see that in action. So we have the buffer pressure, that's simple, but let's run it. As you can see, it spends 5 seconds instead of 8 seconds. That's massive improvements because this time, server no longer slow down by the client. At the same time, the server won't overwhelm the client and do wasted work if the client can't keep up with the server. So it only produce two responses ahead of time. And that's good enough for this simple setup. In the production situation, you might want to experiment the number of the capacity and find the sweet spot for your situation. But this is how it works. So I want to show you the characteristic of buffered backpressure. All right. So this is one more thing. So far, we have talked about many of the patterns we can use to build very powerful concurrent servers and be able to coordinate between the server and the client. But the beauty of the Kotlin language doesn't stop there. So as we identify those patterns and we find some patterns, some kind of structure of the code repeated over and over, you can try to encapsulate that with some customized operators or maybe customized construct that simplify the thing. So actually, there are two built-in operators for flow. One is flow map merging, and one flow map concat. So that's pretty much find in and sequential emit for you, and you don't need to write like duplicate code, like repeated boilerplate code. So that's the beauty of the Kotlin. All right. So here's a summary of the patterns we have covered right now. Hopefully, gives you a rough idea, like this is a long way here, and we have covered many of the patterns, many of the things, and we have the live coding showing the characteristic of each of them, and hopefully that will help you to build your next high concurrent server. All right. Thank you, and I'm ready to take any questions. All right. Any questions? And also, I will be in the Google booth afterwards. So if you have any questions and you want to explore some ideas and want to talk more about the concurrency server, I'm there for the next couple hours, so we can talk about that. And don't forget to use your app to vote for the talk. All right, thank you. Yeah, have a good day.